Hello, everybody. I'm Linda Rossner, Chair of SMPTE Hollywood, and welcome to another virtual meeting from SMPTE Hollywood on virtual production and color science. Thank you to our panelists. I'll have Greg Ciaccio, the co-producer with Brian Gaffney, introduce everybody. And I just want to say that it's wonderful to have all of you. Thank you all. And Greg, take it away.
Very good. Very good. Brian, thank you for co-producing this with me. And I think before we start, want to get some Zoom housekeeping tips out of the way. Most of you have probably heard this before, but at the bottom of the Zoom window, we're in a Zoom webinar, so you'll see a Q&A button. So ask all your questions in the Q&A button. The chat is different. If you want to chat with anyone offline or to the side, please use the chat. Brian will be fielding questions, so please feel free to ask questions and participate. We'll be stopping now and then, so there should be lots of time to answer questions. All right, thank you, and welcome, by the way. Most of you have heard or read about virtual production, or perhaps you've seen a webinar or 10. Virtual production is a really broad term, but tonight we're here to talk about specifically on-set virtual production, or OSVP, also called in-camera VFX. Zach's going to tell you a little bit more about that. We also have a new initiative at SMPTE called Rapid Industry Solutions, RIS, and we'll talk about that. The cool wall chart that is now released. This might be the first time it's actually unveiled in a webinar. But for tonight, even within OSVP, we've got a kind of a targeted segment here on lighting and color science. There's a lot going on, obviously, in just on-set virtual production alone. From previs, VAD, all these things that all go into the new way we're going to be producing for television and feature films. But tonight we're going to talk specifically about lighting and color science. This group here, which I'll introduce, has done a lot of work recently. I've been participating in some of that as well. And they're going to help you better understand how lighting and the entire imaging chain affects the images as seen by the camera sensor. With that, it's my pleasure to introduce Zach Alexander, Paul Debevec, and Mike Smith. Gentlemen, start your cameras. Thank you. All right, so Zach, in alphabetical order, is principal and founder at Lux Machina Consulting. Zach strives to push the boundaries of technology and design in the entertainment industry, focusing on in-camera visual effects, real-time mixed reality, and the future of filmmaking and live broadcast. He works across a wide variety of entertainment formats to tackle complex, large-scale entertainment projects and finds ways to empower Lux Machina's clients with versatile design options, new technology, and unique solutions. Thanks, Zach.
Thank you.
Next, Paul Debevec is Netflix's Director of Research, Creative Algorithms and Technology, overseeing the creation of new technologies in computer vision, computer graphics, and machine learning for virtual production, visual effects, and animation. His 2002 Lightstage 3 system at the USC Institute for Creative Technologies was the first to surround actors with color LED lighting driven by images of virtual locations for virtual production. Techniques from Paul's work have been used to create key visual effect sequences in The Matrix, Avatar, Gravity, Blade Runner 2049, Gemini Man, and others. Paul's work in HDR imaging, image-based lighting, and light stage facial capture has been recognized with two Technical Academy Awards and SMPTE's Progress Medal. Thank you, Paul, for joining us tonight. And yeah, great. Thirdly, Michael D. Smith worked as a digital imaging and intellectual property consultant since 2003. He has worked on projects for many organizations, including Warner Brothers, Sony Pictures Entertainment, DCI, NOAA, Dolby, and DTS. Michael's work on more than 40 intellectual property matters related to infringement and validity of patents has resulted in payments of approximately $1.7 billion. He was editor of the book 3D Cinema and Television Technology, The First 100 Years, published by SMPTE in 2011 and achieved SMPTE Fellow in 2019. He received the BS and MS degrees in electrical engineering from UCLA in 2001 and 2004, respectively. Welcome, Michael, and welcome everyone.
Thank you.
Thanks.
So before we actually really get into the nitty gritty of lighting and color science, we really wanted to kind of talk a little bit more, expand on this big area of virtual production. So we're really talking about on-set virtual production, as I mentioned. There's two kind of competing acronyms, IS, V or IS VFX, or I'm sorry, ICVFX, In-Camera VFX. Sorry, Zach, and OSVP, on-set virtual production. And so I wanted to know, Zach, if you can explain really what that is.
Yeah, so I'm going to take a little short history trip here, and then everyone's going to contradict me once I've gone through it once, but this is at least my kind of view on it. So a lot of this work that I consider ICVFX really has its origins much earlier in filmmaking. And I would even go like, I'm sure there's earlier examples of this, but like if you go to some of these classic old process shots from like Wizard of Oz, where the birds were like they're driving in a car with clearly projection behind them, or that whole tornado scene is on a set with a projection screen in the background, but it's really just using rear screen projection to kind of extend the world out into sort of the background. And I think from Lux Machina's point of view, we entered this sort of field from that sort of kind of very theatrical point of view, where we're trying to make it like we're doing a magic trick and we're doing a stage magic trick, which I think finds its origins in this sort of type of work. So like for us, one of the first big projects that we did was Oblivion, which is really, we were combining our in-camera VFX, sort of thoughts with the broadcast standards that we had kind of adopted doing the large scale broadcast shows we do, because we, do a bunch of screens playback on things like the Oscars or like the Emmys and, you name the multicam award show at some year, I've probably been on it working at some point. So around, I think it was like, let's say 2011, 2013, the live event technology had kind of like gotten back to a place where we could do a passable illusion on screen again. I mean, you'd seen sort of bits of it before, but I think once green screen and CG became, a hallmark, and VFX really entered into its own in the 90s, the pendulum kind of swung away from doing on-set effects. But I think what's interesting, and I know Paul will get into this on his sort of chunk, but like around this time with Light Stage, I think Paul was, and teams like his were starting, or his specifically was revisiting how you kind of do that lighting and make it an accurate representation of a virtual world, versus I think the work that we were doing on things like Oblivion was trying to make it look quote unquote right, just based on, again, more of sort of a, tweaking it using like stage controls, and then leaning into the live performance technology so we can do this like at scale, right? Because I mean, we're doing 100-foot projection screens rather than, smaller, more controlled and arguably more accurate volumes at the time. So for us then, like, I always thought of this work as a continuation of that sort of in-camera special effects that you had seen in that older work. But I think the big thing that comes into it with The Mandalorian and around that time is you see this reconvergence of what was happening, right? Because I think what happened initially was when green screen and CG became the norm, you saw this branching off of VFX and then virtual production from VFX that really started to develop on its own. And quite frankly, the on-set sort of special effects kind of simmered. I mean, it continued for sure, and it's not like it's not a dead art by any means, but like it definitely continued sort of in parallel. So with Mandalorian, I think for us, we see this sort of, again, like I said, a reconvergence of now you're bringing in these sort of large scale theatrical logistics and, and control systems and, being able to hit those markers that you needed to hit to actually be accurate representation of it. So I think part of the funny confusion with all of this is that initially virtual production comes out in my mind, as a subset of VFX, because you're doing work on a stage that will ultimately be part of a VFX shot or a VFX like workflow. And then what ends up happening with like around Mandalorian is there's sort of this, you know, shift as like, oh, this could exist as its own thing in tandem with a VFX pipeline, where you might not actually have to go that deep into a post-production process in certain situations. I would be the first to say that there's no magic bullet here. You can't get rid of VFX or get rid of on-set work. They work best when they're working together. So I think that what we're calling virtual production now is not really what virtual production in the days of mocap and in the original days of mocap and simulcam was. I think what we're calling virtual production now is really a combination of that virtual production plus, you know, these upgraded special effects, you know, in-camera VFX type of work. So for me, that's sort of where we get here. I think the big differentiation between, like, say, rear screen projection is that you have a more immersive and accurate lighting volume. Camera tracking is absolutely, like, you know, what kind of pushes it beyond just being, you know, straight up playback, and, you know, leaning into a real-time workflow where you're working in a real virtual environment rather than it just being like a plate that you can kind of move parts around a little bit, but you're, you know, limited by the constraints of a 2D world. So that's sort of like a broad view, kind of from my viewpoint of how we sort of got here, but I'll kind of leave it to the others then to kind of expand on the stuff that was sort of going on in parallel and ancillary to that, to really like dive into like how to make this accurate and not just like someone like me going like, it looks right, that should be good enough.
Yeah, it's interesting, and I know, Paul, you have also, I think, quite a bit of history that you've experienced and would like to tell the audience as well. But I find it interesting where we started out with in-camera VFX because there was no other way, right? We're now returning to that. There's a little bit of maybe cake and eat it too thing with Ghost Frustum and things which allow you to kind of interleave frames with green screen to potentially have flexibility later. But Paul, do you want to kind of share some of your experiences on the history of this?
You're muted, Paul. Sorry.
I think also getting it good enough is the point of all this, right? So
yeah, no, for sure.
Beyond that, and that's actually what I think the masters of our industry know is what's good enough, and to stop there. Right?
There we go.
Yeah.
My mute button moved to my other screen when I shared, so sorry for
No worries.
Zoom shenanigans.
Yeah. Okay. So let's do a new share over here, and we'll do screen 2, and hopefully we'll have slides on in just a second. Okay. Cool. So hopefully we're good now. Sort of the directions that I've looked at a lot of this work from actually was from the perspective of the very great interest of trying to get the lighting right on actors when they're in a stage situation. And that was motivated by and the work I had done at Berkeley in the late 90s on image-based lighting, where I'd been shooting HDRI maps, kind of these high dynamic range panoramic images. And it turned out if you actually texture mapped a high dynamic range panoramic image around your computer generated scene and then used it as an emissive texture, that it would actually do two things. It would be a kind of a, you know, the in-camera background, because you'd literally see some of that environment in the background, like you can see the UC Berkeley eucalyptus grove here. But since it was high dynamic range, it was all the way around, and I was using a global illumination algorithm to simulate things, it actually provided the illumination in the scene as well. And that helped us put all these monoliths and spheres into St. Peter's Basilica relatively realistically. And I got very interested after that in, could we get basically image-based lighting on live action actors as well? And then we could actually use this as a good way to get better composites for stage shows. And the first thing I tried around then was using video projectors to like reflect onto a screen and then reflect that light back onto an actor from different directions. But I pretty quickly realized that would run into trouble with interreflections if it were actually curved all the way around, and the brightness I could get out of a video projector was pretty limited. So it wasn't until RGB LED units were available that we actually finally built a system that surrounded actors with colorful LEDs. And we could render out versions of virtual scenes and either HDR environments or CGI sets and light actors in real time with that illumination. Now, at the time, there wasn't enough resolution in the lighting that we could put there, so we still used a compositing system to put the background in. You can see some of the composites we got back at the time. Those were actually done using an infrared matting process. So we put an infrared cloth behind, infrared reflective cloth, filmed with a beam splitter camera, and then we could put the mat in there without having to deal with green screen. But shortly after this, I got a call from Digital Domain wondering if we could use this technique to play back image-based lighting on Brad Pitt for a thing that they wanted to test for The Curious Case of Benjamin Button, and particularly be close in on the eye region. And I realized, well, we don't really have enough lighting resolution to deal with eyes here. But by 2004, LED panels were available. And so I sketched out an idea of surrounding an actor with LED panels so that we could play back the light of the different environments they need to be put into. And we found some friends at Background Images up in Valencia who were willing to build this out. They built out one wall. I was hoping that we get to build out the whole thing. But we actually put some of our HDR maps on there, looked at it reflecting off of an actress's face, and we saw that the lighting on the face and the eyes were perfectly successful. And they didn't use that on Benjamin Button, but in various roundabout ways, we did get to be part of the R&D team to figure out how to do the movie Gravity. And Gravity used an LED panel light stage system, the Lightbox, to play back lighting on Sandra Bullock and George Clooney, so that when Framestore did their amazing visual effects of compositing them into the virtual space suits flying around the virtual space telescopes, the lighting was very close to what it needed to be. And as a result, the effects were incredibly believable for that. And nowadays, surrounding actors with LED panels has become a quite common practice. Here's an example from from Netflix that's been put together in Studio Babelsberg. It's a huge LED panel stage surrounding the actors, maybe 270 degrees around. There's LED panels on the top to get the lighting coming from there. And it seemed at this point that with the density of LED panels, you can actually use them for the in-camera backgrounds, as people have been doing for backgrounds, and also putting other ones in other directions for lighting. But there's been so much focus on the in-camera background and certainly interest and remarks that it helps with the lighting. It seemed like it would be a good idea to maybe test to see how good these stages are at actually reproducing lighting conditions and doing image-based lighting where you really get the right result that you're hoping for. And that was the idea behind a test that we did at the USC Entertainment Technology Center in lighting reproduction. That some of the collaborators are on the call here, and some other ones are listed on the slide. But the basic idea was to film actors in a couple of real environments, record the lighting where they were using HDRI maps and mirror balls and such, and then reproduce that lighting by displaying those lighting environments in a LED lighting stage that would then let us test how close do they look on the stage to how they actually looked in the real environment. And so we shot our environments. We got 4 of them at a studio called Riot. We got 2 interior environments where most of the light came from the front, for example. For each of those, we went in with an HDRI map, capture with a fisheye lens, different directions, got 360 HDR images. Eric Winquist at Weta assembled our HDRI maps for us, which felt like we had a very high-end visual effects company working on our project. The maps also provided the ability to illuminate digital objects with measurements of that light. Here's our side lit environment that was an interior. We went outside and got people in the shade for kind of different color temperature and spectrum of illumination. And just to make things really easy on ourselves, we also shot in direct sunlight. We did all the things that you need to do, including special ND filters, to get the full dynamic range of that lighting environment represented in the HDRI map, so it reproduces the appearance of the spheres pretty accurately. But we knew we'd probably run into with some trouble, at least with this one in the LED stage. And the LED stage that we tested on was this very cool, very new one at line 204 up in Poicoima, thanks to our people who made that possible down here. And we wanted to use it, really for lighting. We needed to know that the radiometry and the geometry would be correct. It was a little bit tricky to verify that the stage was actually displaying linear values. It took a bit of a hunt after we realized that our color charts weren't quite radiometrically accurate to what we were measuring with a light meter and what they should have been. And we found out there was some residual tone mapping function that was getting applied that we needed to turn off before that was kind of right. And the other thing that was tricky was to get the geometry, the projection geometry, so that angles that were coming off the light probe would end up being the same angles of light incident coming from the LED stage. And after getting a good calibration pattern on there and debugging some stuff, we were able to verify that as well. And then we did side-by-side images, tried to set up the same thing. Unfortunately, one of our actors, we couldn't get the same actor the following week, so we tried to match skin tone. And this is our kind of real versus synthetic comparison. On the left, the real actors in the real library at Riot. And then just out of the box displaying this HDRI environment on an LED stage as best we can and taking a picture. And as you can see, the ratio between the background and the subjects is off. The overall kind of color balance of the subjects is off. Colors seem to be a little bit different. A lot of things seem to have gone wrong. But we didn't want to just stop with that. We wanted to find ways to mitigate this and improve it so we can get good results with these stages. So when we were in the stage, we actually looked at rephotographing inside the stage an HDRI map of what the stage was displaying in terms of lighting compared to what was actually captured in the real locations. And by looking at that, we realized we could debug some things. Like, for example, looking at this HDRI map from the actor's perspective, we realized that the major source of illumination was coming from the front. And that was kind of exactly the lighting directions that weren't represented well or at all in this LED stage. Most LED stages are open in the front so that it's not as much of an echo chamber and cameras can roll in. Turns out often a lot of important lighting comes from the front. And so we decided we could probably get a better match if we used the stage as lighting rather than, in this particular case, in-camera background, and turn things around, put some green screen behind the actors, and then use the entirety of the stage to light the actors. And we tried to see if we got a better match. And we actually did get a much better match by doing that. We haven't done the composites to put the background in there yet, but you can see zooming in on this that the actors match quite a bit better. There is this effect that darker skin tones tend to shift toward red, lighter skin tones tend to shift toward pink, and something weird's going on with Eric's shirt in terms of the color rendition. We found we had pretty good luck with the side lit scene. Looking at it closely, we thought key to fill was a bit off, that some of the interior lights, the specular highlight wasn't quite as bright as it should be relative to the other lighting that you can see over here. So again, we looked at that, the HDRI maps of what the stage was actually producing versus the lighting that we intended to put in. And here, the lighting directions were represented pretty well, but it turns out there was clipping. If you stop both of these images down, the original HDRI map shows the full range of illumination that was there, including the light streaming through the windows from the sky, whereas all that was clipped in the LED stage. And not surprising, the lighting would be off. So what we decided to do here is that there was about 4 more stops of light that you could see in the sky and on the LED lighting that was part of the environment, the practical LED lighting. And that if we just displayed the HDRI map in the stage super dark, we actually went down by 4 stops. We're pushing contrast ratios a little bit here. The panels are doing their best to do the dark tones. The in-camera background would probably be compromised at this point, but now we basically got the full range of light without clipping. And the result was that the lighting reproduction improved considerably. And things like the specular highlights, the overall key to fill ratio is a lot better. You can see, particularly in our subject on the right, you can see a specular highlight from the interior light there. It's matched pretty well with what we had over here. But again, color rendition is off. Skin tones are off. The the costume is off. Let's go outside. This one worked pretty darn well out of the box. Basically, the dynamic range of a cloudy scene can be represented pretty well in an HDRI map. In the way that we showed it in there wasn't any clipping. And as a result, these matched quite well, other than still this color rendition issue of skin tones and clothing that we've got. And then finally, for the sunlit scene, we knew this was probably going to be a problem because there's no way an LED panel can go bright enough to be the sun. And so if we just put that clipped HDRI map on our scene, with no surprise, the illumination in the LED stage didn't look like it was sunlit. You know, the reflection in the mirror ball looks pretty good and pretty similar to what you have here, but the reflection on the gray ball, very diffuse, versus here you see like the sharp sun shadow. The faces look totally different as well too. And so we wanted to improve on that. One of the things that we had suggested back in the SIGGRAPH 2002 paper, if we ever did build a big LED stage system that wanted to get the lighting right, is you probably need a special case light source to simulate the sun. And very fortunately, Tim Kang, one of the big collaborators on this project from Quasar Science, brought in an excellent 1x1 light source, which we then cast in the role of the sun. And we placed it just in the way of where the sun should be relative to the subjects. And Tim measured the key fill ratio, had measured the key fill ratio in the real scene. We set the light so that it basically matched that key to fill ratio. And lo and behold, we got a much improved version of the lighting reproduction in the stage. And in fact, actually what I would call quite a close match between the illumination that we saw out there in the real world and the light that was reproduced on stage using that special case sunlight. And another magical thing happened, which is that all of a sudden the skin tones matched a lot better. And the shirt, the colorful shirt, matched a lot better too, all of a sudden. That was one of our biggest problems. Like in the shade scene, skin tones were off, and we had this reddish shift, pinkish shift. And then the shirt, particularly the orange spots on the shirt, just basically go reddish in this version. And so what's going on? Well, what's going on is that when we simulate the sun, we simulate it with a broad spectrum light source. It's an LED that uses phosphors to try to fill in a lot of the spectrum. But the lighting that we're using in the LED stage is made out of red and green and blue LEDs. This is actually the spectrum that we measured back of the light stage in 2002, which uses essentially the same spectra. And we already realized that there was this color shift problem. The spectral similarity index, which measures how well a given spectrum can match daylight or tungsten light that we're used to, and it's pretty broad spectrum, is actually very poor for solid state, for RGB LED panels. It's actually 29 out of 100 for the SSI. And this is a problem, particularly for things like reflectance of human skin, because if you essentially are lighting with red and green and blue, it essentially shifts the response function of your carefully crafted camera sensors, that now your camera sensors are basically just sensing these as like it's red response, it's green response, and it's blue response. It's not exactly true. It's basically what happens. And interesting things that happen in skin spectrum that happen between green and red just don't get recorded because we're not generating any light there. We're just querying things right here deep in the red spectrum where the skin is reflecting a lot of light. And that's why lighting with red RGB LEDs gives people kind of this pinkish reddish cast compared to proper broad spectrum LEDs.
Hey, Paul, real quick.
Yeah.
Just FYI, Tim is in the house, and if there's any questions that come up where we'd like him to address them, and we can just quickly pop him on.
That would be fantastic. Awesome. Tim is the expert on this stuff here. The orange shirt patch, also I took a spectral measurement. Turns out it has a very similar spectrum to human skin with this big drop off between red. And then by the time the green samples, it's quite low. And so that's why under RGB lighting, it looks basically like a red sample, whereas under broad spectrum that actually queries all this reflectance you see up here, it's going to look orange. And that's not a color shift that you'd like. We were trying to figure out how to address this in our work after the first light stage work. And in 2003, we started building LED light sources made of multiple spectral channels. So this is a red, green, blue plus turquoise, amber. We had to put gels on top of white LEDs to get some of the spectra. There's an orange LED. So we made a 9-channel light source, and we showed that if you do decent math for how to drive your 9 channels to simulate different kinds of spectra like daylight or tungsten fluorescent, you can get quite a close match. Whereas if you do it naively with an RGB light source, it can look basically terrible. And by the time it was time to work with Chloe Legendre in our USC lab to do her PhD thesis, we had built a multispectral light stage where we were surrounding actors with at least 6 channels of illumination. Red, green, blue, amber, cyan, broad spectrum white. And by shooting color charts when we were out in our environment, in addition to the HDRI maps, we found a way, pretty simple math, to drive all 6 channels of illumination so that it reproduced natural lighting condition pretty naturally. So on the left, these are 2 subjects who are lit by real lighting of the real world, broad spectrum illumination. We captured the lighting, we reproduced in the light stage. We got a good map for them to composite them in the background. And it looks very close for how they looked standing in the light stage on the right to how they looked in the environment. This is with absolutely no manual color correction, straight out of the algorithm. We'd love to have that kind of capability on larger LED stages. For example, we built one in 2017 for sous vide visual effects in China that's all made out of these multispectral lights. And they've used that on a few hundred episodes of television and several Chinese motion pictures to get the lighting right on actors that they want to virtually insert into scenes. So it'd be great to do this with LED panels as well, but unfortunately LED panels, which are designed for display, are, and we're going to hear some more about this in the next presentation, I think, are kind of designed for this wide color gamut. It doesn't really matter for display purposes if they fill in the gaps, because you can fool the human eye it's looking at yellow by just showing it some red and some green at the same time. But you can't reproduce the lighting the way that it would reflect off of other stuff. So it'd be great if there were LED panels that included a white LED or an amber or yellow or turquoise LED. And there's actually, these exist, but just kind of like in small hobbyist form, where there's packages that have both RGB and white for every pixel. Wouldn't it be fantastic if a panel manufacturer took on the task of producing a good color rendition lighting instrument version of an LED panel, and we could use those in our virtual production stages. So let me thank the collaborators again here, and there's going to be a paper and data to appear from that lighting reproduction project on the USC ETC website here later this fall. Thanks for the time.
Thank you, Paul. And yes, a lot of this work has come out of the ETC side. I've been lucky enough to work with Eric Weaver and Horst, who run the working group. And again, thank you to Tim Kang, who's now joined us as a panelist. We sometimes rope people in. Pete Luday and Eric Winquist from Weta. Thank you. There are many others as well. By the way, it was really funny, Zach, when I first met you in Lux, we were taking a trip down to your place for about a year and a half ago. I think it might have been for Lost Lederhosen HPA. And I arrived and said, and I texted Tim Kang and said, Tim, do you know Lux Mocking is right across the street from where you work at Quasar? Like, you should come over here. And it's interesting because, we're talking, Paul's talking about using these for reflections and not in camera. And now we've got these panels that were originally designed for live production. I mean, look at the state of our industry. The game engine is designed for gaming. The panels were designed for live concerts and signage and things like that. And now we're all trying to make them work in a way that is color accurate and that works the way our industry works with proper key and fill. So you have these displays that are kind of functioning as lighting and as displays. So Tim runs the lighting committee at the ASC, and I thought it'd be great. He's just amazing in getting involved in a lot of this. It's a rabbit hole for sure. But Tim, I just want to thank you. You can pop on actually as we talk about this, because I think it'd be great if we have any questions about the lighting part. You can kind of chime in. And if anything, we're about halfway through. We have a lot to talk about. I wanted to ask Zach, is the work that you're doing at Lux. If you want to just explain, most people know you out there, but if you can explain what Lux Machina Consulting and what Lux Machina does.
Yeah. So, I mean, originally we cut our teeth on doing large scale multi-output video systems for broadcast. And so like I said, like before, like on award shows and stuff like that, there's a bunch of screens of varying resolutions all over the stage and stuff like that. We would design the systems that would do that playback, because often it was a design being driven by production design and then being told, okay, well, how do you actually get content there? So that's sort of where we started. And then kind of getting into more of what we do now. We still do that work for like live corporate events and stuff like that. Obviously, pandemic made that type of work a little bit less the last couple of years or so. But what we focus now in terms of, doing like the volumes and things like that is we do offer, and now that we're part of NEP Group and paired up with Halon Entertainment, we actually provide a full virtual production pipeline from previs all the way up to post. And like Halon does some like post-viz stuff, but like from Lux's point of view, we really want to stop after production. Like I think our big advocacy here is that there's all these sort of different ways to do it. We don't want to create a black box. We want to be able to kind of do all input and then output that everyone can sort of understand. And so with that, like the current tools that we're using are, LED walls, various camera tracking systems, and like the Unreal Engine currently is like they have the fidelity, they have a huge focus into virtual production tool sets and things like that. So we're doing a lot of work with that. So you would come to us if you had a production, or we're starting to build our own facilities that you could actually roll into and, basically provide those on-set services. And quite frankly, taking the work that like Paul and Michael have done and like being able to go back to people like them and say, yes, we actually did the thing you wanted us to do. And here's the data that like proves it, or here's where it specifically dropped off. And this is where it has to be addressed in post and things like that. So we kind of just are one of the groups of people who have just been hitting our head at the actual practical use of this for many years. And so it's a lot of just operational stuff.
Yeah. And you were mentioning also that Lux, it was actually in the Q&A, building these stages, leveraging multiple shows for studios, because obviously, we've got tech that's not cheap, it's expensive, and it's evolving rapidly. So it's funny, it kind of dovetails into a lot of the other part of virtual production, which you could call remote production, which is working on a production before you're actually on a stage. It ties in perfectly, because with the expensive stage time, you're going to want to simulate or work in a virtual environment as much as possible. And that's really the kind of the larger side of virtual production. Yeah,
well, and it's important to realize too that a lot of this stuff is scalable. Like, I mean, people forget sometimes that like the reason the Mandalorian volume was the shape it was, like there was a lot going into it, but a big part of the reason was their main character has a mirror ball for a head, right? So like you have to get reflections from all over the place. And like, yeah, there was a whole bunch of other stuff that went in. I don't want to diminish like the work that went into something that big, but like if you're going into it and your entire cast is wearing like furs and animal pelts or something like that, like having super accurate reflections everywhere is less important than having realistic lighting. And like looking at Paul's like light stage is a perfect example of like, you don't need, millimeter pixel pitch stuff to get to a realistic looking place. And so like, I think it's just important to look at all this stuff and know that there's always a spectrum. You don't have to be locked into the thing that costs, hundreds of thousands or millions of dollars to do. It's really trying to use these learnings and use these types of workflows to just kind of be able to ultimately capture more on set rather than, shooting a whole day and going like, well, I hope that'll look good in 3 months. Because that's like
exactly. Yeah, and there's the different approaches, right? Paul basically designed a solution for a particular problem versus just building a volume and saying, okay, there it is, let's use it somehow.
Yeah.
Exactly. People like, you've got Stargate, who basically, in Sam Nicholson's company, it's bespoke, it's for the job. So if you're shooting out of a window in a car and you just a 75-inch 8K display will do it, then great, let's use that. It's different tools. Brian, is this a good time to stop for some questions, or
there's a couple of questions coming up around calibration and color and calibration of the walls that I think might be addressed by Michael. But before we move on, Paul, there was a question during your testing, from Benjamin Buttons to where you got with the skin tone matching. Did you do any testing with makeup along the way? Was there a hair and makeup process that went along with that? And did you see how the makeup's affected? And with all this new lighting, is there a new technique that needs to be thought of in the makeup for the reflectivity, and can that help?
Yeah, that's a great question. And I believe in our 2016 test with multispectral lighting reproduction, both of the subjects were wearing makeup, just like the normal makeup you might wear during the day, and it worked fine for that. I think generally speaking, makeup will lessen the spectral dip from where the hemoglobin starts absorbing the shorter wavelengths. Kind of guessing. I haven't looked at the spectral plots here. So putting makeup on people might make things look easier. Yeah, a little bit of cinema history or television history in the black and white TV days, skin tones, looked a bit odd, even in the black and white projection on the TV. And special makeups were developed to make people look good on black and white television. I believe Max Factor was one of those. This is my friend X-Ray Halprin, who is a former visual effects person, telling me about this. So it's also entirely possible that someone could develop a makeup that makes skin tones look good in LED volumes, even without the rest of the spectrum being generated for that, and that could be a helpful way to go forward. The problem that we're dealing with, even in all the color science that gets the in-camera background to look perfect, exactly like the pixel values in the Unreal Engine projected on the panels look like exactly the pixel values in the camera that you want, will also be the wrong lighting to get skin tones to look right. They're just opposed to each other, unfortunately. So yeah, maybe makeup is a good solution for that.
One thing that clear, it seemed like for years of darker skin tone shifting into the green, it looks like LED panels is actually a potential answer, to keep skin tones with a balanced color and some red, especially on the darker skin tones. What's your correlation to that? Do you have need for mixed lighting, and is LED lighting for reflection and sort of bounce up the skin tones an answer to various different actors that may have different skin tones on the set?
I think this is a good question for Tim Kang, who's definitely been thinking about this and designing lighting instruments that help out with this quite a bit, I think, if Tim's available.
And cue Tim Kang. Not bad.
Hi, everyone. Can you just restate that last question again?
It was more related to the skin tones. If you have a set now that may have dark skin tones, white skin tones, all different, blend of, the cultures out there. Do you find that now mixing that with different light panels can help with that? Going back to the makeup combined with the lighting to get reflections. It was clear that some people were shifting red, and some people, it didn't look right, and some people look great. So can you mix those on set, and is there any experience in that?
Yeah, it's a very good question. If you're lighting with just those RGB LEDs, and I answered the question elsewhere in the Q&A, but because they're all generally the same RGB diodes or similar RGB diodes used in all these panels across companies. But the problem is that skin tones are supposed to have nuance, right? They're not just a single tone. There's there's blush response, there's all sorts of things in the skin, and then across different ethnicities, those nuances also are very different, and they're subtly different and instantly recognizable. And the problem with RGB is that it removes all that nuance. So actually, it's the opposite. It makes everybody look too much the same. Maybe tonality in terms of the brightness difference, but the color ends up mushing into the same kind of reddish, garish sort of looking color. It's just different levels. It's not necessarily a good thing. So it's really more using broad spectrum, and as Paul said, filling out those gaps so that you can see those nuances appear, so so that the camera sensors can pick up on those nuances.
The appeal, honestly, with using LED for like reflections over, say, like projection, as Paul kind of like alluded to a little bit, is that just like there's a brightness factor where you have more of a dynamic range that you can play with. And like there's some other weird mapping stuff with how Unreal, if you're trying to do that kind of version of things, but like I mean, we've used on shows projections for any number of years and still do for certain things, but like the LED, you just get more punch at the end of the day. So like in a perfect world, like we were talking about before, it's like we either want the RGB AW or 6-channel RGB thing, but you've got to, like when you look at the LED walls themselves, like the component parts are made by a surprisingly small number of factories. And like what's really happening is if you look like at these bigger companies, the LED panel manufacturers, is they're really going out into the wild, finding all these different companies who have the parts, and then based on, you know, they're mixing and matching their version of existing things to make their particular product, right? Which is fine. There's nothing wrong with that, but it's like, they're all making separate choices based on like cost and fidelity and, you know, matching batches and things like that. So like at the end of the day, to like what Tim was saying, when you really get down to the nuts and bolts of like the actual component parts, there's really less variation than you would think.
Yeah, and not only that, I mean, when we were dealing with traditional camera display issues, we had a reference monitor. So be it the you know, BVMX 300 display, and you've got an Arri Alexa LF. And a cable that goes between them, and a player, of course, to see it. We've got the camera, we've got the player with the Unreal Engine, we've got the artwork that goes into it. It had to be mastered a certain way. It's running on a computer. So as we found out with Paul, like we had some sort of Windows desktop sizing that caused some issues. So talk about your gotchas. And then you've got the interconnects. Are you going, you know, SDI or HDMI? It turns out HDMI is preferable these days for running those signals. And with all that, you've got processing on top of that. There's so many areas that have to be checked for Unity.
And what's interesting is like, that's one of the reasons, like from our side, we kind of got this initial leap of like, it's that last 10% after getting it 90% of the way there. That's the hard part, because like, when we were doing stuff that was based like purely on broadcast gear and standards and stuff like that, where we were on like HD SDI as opposed to HDMI and things like that, the reason that stuff was so easy to put together was because of all these SMPTE standards in terms of like how they're actually supposed to talk. And it created a baseline for all of these different hardware manufacturers to make things that just hit these specific specs. And the problem is we're now trying to do that with a set of hardware that, like, I mean, you look at gaming, like gaming cards and stuff like that, and watch videos on YouTube. If they have like a frame rate meter, they're like, oh, I hit 120 frames for a couple seconds. Like, there's no film set in the world where you're like, oh, I hit 24 frames for a few seconds, and then it like went all over the place. Like your DP would go insane. So it's just you're mashing together things that were never fundamentally designed to do any of this. But like, it's definitely changing very quickly. So it's very exciting.
Yeah, and Michael, it's
yeah, I think the point is it's close enough, it's good enough, right?
Yeah.
So that's really an important thing to keep in mind with all this.
Yeah, and obviously, you know, we've been doing some work. You guys have been doing it quite a while under Mike Zink with Pete Luday on the color science stuff. I know you have some stuff to show and tell, so I'd love to hand it over to you.
I'll put that up here. Let's see.
Great stuff in the Q&A, guys, by the way. Thank you, everybody out there, for asking some questions. Got some great items in here.
I got basically some different test results to share with you from some work I've been doing with Warner Brothers, with Mike Zink and Pete Luday, also with the help of Arri and the ETC folks also. So just jump through this. Just have an overview. I'll talk about a couple different topics: LED spectrum and color gamut, viewing angle, dithering, a little color test we did with a test chart, and a teaser for our SMPTE fall conference paper. Sign up now. Just stepping back, just way back, in case people haven't had the background to get up to speed on what we're talking about here. If we look at the spectrum of an LED, basically there's a peak and there's some bandwidth that falls off and eventually goes to zero. And so if you have a plot like this, this shows the intensity on the y-axis, and the x-axis is the wavelength. And so like politics, you've got red on the right and blue on the left and green in the middle. And so so basically this is just a sample spectrum of a green LED. There's a parameter called the center frequency or the dominant wavelength. In this case, it's 550 nanometers. The LED elements can be parameterized by these. You can get them from the manufacturer in a certain configuration. And there's also the full width at half maximum, or FWHM, which is the bandwidth at half the maximum, basically 50% down from the peak. And so this is 60 nanometers in this case. If we make the bandwidth narrower, the full width half maximum shrinks to 20 nanometers, for example. And we can also change the center frequency or dominant wavelength. And these would be basically picking different LEDs from the manufacturers. I have a little quick video that I made that shows a simulator I built actually in a spreadsheet that describes how the bandwidth and center frequency of the red, green, and blue elements affects the achievable color gamut of the display wall. So I'll try to play that here. Of course, didn't check the box. Hold on a second. Oh no, it is checked. Okay. Okay. This shows a spreadsheet simulation of the effect of dominant wavelength and spectral bandwidth on achievable reproducible color gamut. On the left side, the spectral output of the red, green, and blue LEDs are shown in addition to the sensitivity of the XYZ color matching functions. On the right side, a XY chromaticity plot is shown with visible locus, Rec 2020, P3, and Rec 709 color gamuts in orange, blue, red, and black lines, respectively. The achievable color gamut that corresponds to red, green, and blue LED spectral output is shown by the green dotted triangle on the right graph. In this example, we are starting with the parameters of a commonly used LED wall with dominant wavelengths of 470, 520, and 622 with corresponding full height half maximum bandwidths of 20, 35, and 18 nanometers. It has a large achievable color gamut, but it doesn't completely overlap any of the common video color gamuts. If I change the spectral bandwidth of the green LED to be more narrow by lowering the full height half maximum parameter from 35 nanometers to 15 nanometers, you can see the achievable color gamut increases and the green primary gets more saturated, moving away from D65 white point and closer to the visible locus boundary. If I increase the spectral bandwidth to make it broader spectrum by increasing the full height half maximum value to 50 nanometers, the achievable color gamut shrinks such that Rec 709, the black triangle on the right, has less overlap with the achievable color gamut with these dominant wavelengths and wider LED spectral bandwidths. If I change the dominant wavelength to other frequencies, for example, 462 nanometers, 545 nanometers, 625 nanometers, the achievable color gamut includes all of the Rec 709 gamut and most of P3. To get the whole P3 gamut, I can change green to 538 and red to 635. This simulation should help explain the concepts of dominant wavelength and spectral bandwidth and their impact on achievable color gamut. Okay.
Very cool, Mike.
All right. So hopefully that gives you some intuition there on how that works. And so this is the other side of it. So this plot shows the different spectrums of LED walls that we measured showing D65 white versus the daylight spectrum from, the reference spectrum from the SSI metric calculator. And you can see how the peaky spectrum does not look like the broad spectrum of the white LED. And so there's a trade-off, the wider the gamut, the narrower the three primary spectrums are going to be, but the worse they become for lighting, which is what Paul and Tim and Zach have mentioned. So anyway, this is just an engineering trade-off that's being made, and I think the walls we're using now were not made for lighting. They were made for displaying images on the side of the 4 or 5 freeway or something like that. So That's where this is coming from, and the quality is getting better and all this stuff. But that's really what. Anyway, they're not made for lighting, and hopefully someday soon they will be, and we'll be able to use them. So another another piece of information that's interesting to study is the viewing angle performance of the LED walls. So this is some examples of some measurements we took of a popular LED wall, showing native red, green, and blue and white full screen, and looking at this off axis, actually little patches on axis and off axis. So basically we point the camera at the screen to get the 0 degrees from surface normal. And then we actually, in one case, we moved the camera off axis, and the other case, we actually moved the screen in different testings we've done, but it's equivalent. And what you see is that there's of course a fall off as you go farther and farther off axis, the luminance drops off. And so, but what's interesting also is the luminance of the red, green, and blue elements drops off differently if you go to the right versus the left in this particular configuration. And so this causes a color shift to actually be introduced as you go off axis, in addition to the luminance drop off. So the color balance of say white, for example, will change. And so the plot on the right is a chromaticity plot, Y and X chromaticity, and it shows how the chromaticity changes as I moved, as we move through the measurements from plus 60 degrees, plus 45, 30, 0, and then going the opposite direction in negative degrees. So anyway, so that's pretty interesting. It's something that also varies a lot by manufacturer, and also there's a different performance horizontally and vertically. Most of the time, people care most, at least in our application, mostly they care about horizontal viewing angle performance, and so there's generally more of an optimization of that compared to the vertical. But if you do measure vertical versus horizontal, you will see a difference for most products. And here's just an image of the visual impact of this. So on the right, I basically have the patches of the white that I filmed. There's a little thumbnail of the actual patches. This is on the center one. 0, negative 30, plus 30, negative 45, and 45 and 60 and negative 60. And so when you put them on top of, when you put those out, so basically I took 2 sets of footage, one in focus, one out of focus. And if you look, we're looking at the out of focus patches now, so you don't see the moire from the LED elements. If you look at it on top of black, you don't notice the difference. But if I take the center patch, the 0, and basically stretch that color across the whole screen, and then composite in those little patches on top of that, you get, the reference 0. Of course, you can't see the little squares, but at 30 and plus or minus 30, plus or minus 45, and especially plus or minus 60, you can see that the luminance is dropping, right? But if you look at it carefully, you can actually kind of see a color shift as well, especially with the 60 versus 60 plots. So that's an example of the impact. So when you're doing measurements, it's always nice to be grounded in reality of, is this good enough or is this close enough? And so, if this was important to you, you would try to keep it so the wall wasn't showing something continuously, really at wide angles. So another practical test we did was to do a basically a practical colored paper versus the LED wall at different viewing angles. And so in this case, we set up a nice light on a piece of colored paper that was on axis to the camera on the left half of the screen. And on the right half of the screen is the LED wall. And I quickly tried to visually match them in the stage just by eye. It's not the most perfect thing, but basically once I got the color matched for the on-axis test, I didn't change it for the other ones. So relatively, you can see the differences. So this is a video showing 3 different types of colors, and you'll see how it changes. So it's not moving; it's just a video of footage we took with happens to be with the area camera. So you can see that off axis, there's quite a big difference, and 75 degrees is quite a big quite a big angle. So probably don't want to go there, but that's just another. It's a quick test to show, but it was quite a lot of work to set that up. Let's see. Okay, next slide. So another thing that's really important with these walls is something called dithering, which improves the luminance tracking performance. And so the LED walls, they can't continuously fade up from black. So they have sort of discrete points, and I think it's like 13 bits or something of discrete points in the luminance processing. And what that looks like, especially in the coming out of the shadows, is these big quantized steps. And so basically, if you put an input signal in going from 0 to 20 10-bit code value, if you don't have dithering enabled, you get this green line. You get basically no output from the wall. And then when you go at code value 23 or whatever, it finally jumps up. And then it's the same luminance value, even for different increasing code values, and then it jumps up. And it's very discontinuous, and it leads to what's called banding artifacts that you probably are familiar with. So dithering basically trades spatial resolution for luminance fidelity resolution, and is especially helpful down here. And so when we turn that on, which is implemented in this processor, you can see the orange line matches almost perfectly the reference EOTF curve, which is really good for making good picture quality, especially because in general with display technology, like when we're watching displays, not with filming them, the shadow coming out of the shadows and coming out of the black is a really important part of image quality. And so anyway, it's still relevant here. And so I have an example here. So this is a picture. This is filming a static image in the background on the LED wall with Mr. Zink in the foreground being lit, and maybe a little bit too much for a night scene, but we're just amateurs here. So anyway, so we're just doing this test. So what you can see is with dithering on, you can see much more shadow detail here than with dithering off. And so that's consistent with the measurements. It makes sense, but here we have a sort of an actual demonstration of the value. So that's another important thing. It turns out that dithering, basically the type of noise you use for dithering really can improve the results. And so the really good dither algorithms that are implemented use what's called blue noise, which is a special type of noise that doesn't have low frequencies. But it goes back to I think it was invented in the 80s. So it's kind of cool to see that being applied today. Another thing just to share, we did a color test chart of practical versus LED Unreal. And so in this case, we have an LED wall in the background showing an image from Unreal that's being rendered by Unreal, and a foreground lighting, a foreground object, the color charts in the foreground being lit by some nice airy lights. And we tried to match the parameters of the lighting into the Unreal Engine and the camera settings and the Unreal camera settings to match the camera settings of the area camera. So this is the result, and here we go. So there you go. So that's close enough, good enough maybe for some people. But this was also open loop, so we didn't do any additional calibration to really make it match, like force it to match with signal processing. This is just open loop, trying to simulate it accurately in Unreal and trying to film it and know what we're doing on set with the lighting values and the camera settings.
And that's a black pearl too, yeah.
Yeah.
Well.
Yeah. And then I have a little teaser for our upcoming work. We've been, as part of this work on studying LED walls, we have a SMPTE paper coming up next month, and it'd be great if you guys could join and register. So I'm just going to quickly give you a teaser. Basically, looking at the color rendering pipeline, if you look at the viewing transform has a big impact on what you see. And especially when you have incredibly bright saturated backgrounds that you can actually get from LED walls, which normally don't exist in the world, you can see a difference. So if we use a standard LUT, we get the pink look whereas on the right side we get the red. And then if we just cycle through these, this picture time tells the story. I also think it's interesting to see the difference in color between the shadows. The lighting is blue in the wall. It's lighting his face, and on the side with the deep shadows, it's actually blue. But on the wall, it looks cyan with the use of standard LUT. So on the hue preserving side, which is a different LUT that we basically tweaked the standard LUT to make it hue preserving. And in this case, the shadows and the lighting in the shadows matches the background. Also, out of focus, you also see some colors changing in the out of focus regions that in the standard LUT, which doesn't happen in the hue preserving LUT. So anyway, go register for that conference. So anyway, that's the material I have. So.
That's great, Mike. Thank you. Yeah, that was a lot of fun testing. Some things that we tested for, some things that came up that we did not expect, which happens. Okay, we're heading. We're at 1 hour and 8 minutes in. I mean, we always try to keep these. We target for an hour, and they often go an hour, 15, hour and a half, depending on level of interest. We still have 90 on there. I think we hit over 100, which is great. Are there anything else? I did want to briefly talk about SMPTE's RIS initiative, but I don't want to do that unless there's anything else. I see there's one other question in there. It looks like a perfect Tim Kane question from Danny. And then I guess Jim just posted one. Brian, do we want to go through these?
I had one comment to make too.
Zach,
in the chat. Please. Just yeah. Oh no, I was just gonna say, like, there's talk about, like, possible 16-bit chips and LEDs and stuff like that. I think the thing that's just really important to put out there is that, like, your whole chain has to be able to do it. And, like, the truth is that a lot of the LED walls can actually do much higher bit depths than, like, just from a mechanical point of view, than the processors or the graphics cards that are feeding them. And so, like, this is another huge problem for us, is, like, you are limited by certain things in HDMI 2.0 and things like that. And it's just, it's always, it's just a rabbit hole every time you look at one thing. Like, the ultimate answer here is that there would be some magical manufacturer who is making both the camera, the wall, the processor, and the graphics card. And none of them would have, like, frame buffers, and they would all just be like one giant machine that you would just, like, point and use. But, like, yeah. So just be wary of anyone who's like, oh yeah, this one part, it totally solves the question. Yeah. It's like, no, man, it's got to fit into everything else.
Totally.
I have some more nuance to that as well, and I said that in chat,
sure.
but I'll just bring it up here. Is that, when they're talking about, let's say, 16-bit, it's not necessarily available to you as the person sending information. It's 16-bit driving the digital to analog conversion. So there's always going to be an attrition of data, first of all, so that eventually, after thermal calibrations, color shift calibrations, and just general linearization calibrations, all these sort of things, it steps down the amount of values you actually have available to you to use to drive the actual LEDs. So that's one thing. And the other problem that I've encountered a lot is that there's sometimes a trade-off with these driver chips. They'll say it's 16-bit, but in order to go 16-bit, they have to reduce their PMW rates. So you might try to enable it, but it'll end up increasing flicker and be unusable on camera. Yeah. So then you would then have to all of a sudden go down to 12-bit. And then all of a sudden now you're seeing lots more banding, because with attrition of values, then you only actually have an 8-bit display, or maybe even less.
Free ever.
So yeah, there's nothing. You have to be very, very, very wary of these sort of specs when you're looking at these panels, because you have to really, like, kind of do your homework to really see, like, what actual effective data you're actually able to send to the wall. So that's a really, really, really critical thing to question. So,
yeah, great point, Tim. Paul, you have a point here. Oh, you're muted, Paul.
Michael, thanks for a great presentation. And I loved seeing, how you kind of bring up the point that, if you optimize for gamut, you end up producing narrower peaks further apart, which is exactly the opposite of what you want to do for color rendition, basically. So we have these two.
The perfect primary is a laser with Rec 2020. It's just
right. That would be like the
not
worst.
what you want for lighting. Right?
That's gonna be the worst for lighting human skin. I was wondering also, from my understanding of how LEDs are actually made, there's like fundamentally like one kind of electronics technology that creates the longer wavelengths, and there's a different kind of fundamental electronics technology that creates the shorter wavelengths. And of course, then there's the whole stuff that happens with phosphors to make the shorter wavelengths white. But ignoring that, I always thought there was difficulty in producing bright, efficient LEDs in the yellow area, which we jokingly called the Uncanary Valley. And is that still the case at this point? Is that hard if we wanted a primary that was right in that yellow, right between green and red, that would maximize how much additional color rendition we could put in if we got a fourth color channel? Can anybody even make that?
Yeah, it already exists. Yeah. The bigger issue really is more green diode, because the green diode is great for, as Michael mentioned, the overlap for the CMF, the CIE 1930 CMF, right? But the green diode generally lives on the crossover point between the blue and green channels in most digital cameras. So that causes all sorts of, that's the source of so many woes and problems that everybody always sees and talks about. So if you can get that green diode to shift over, if that could be invented or created or implemented, then yeah, that's a big thing. Because then you can use, there's a cyan diode too. So then if you get a blue cyan, if you do a 5-chip, blue, green, cyan, amber, yellow, and red, then you can really at least approximate all the top issues you were talking about, Paul. So
no, it's just, and it's also like there's also the challenge of just convincing the manufacturer to do that, because like the uncomfortable truth of all of this is the amount of LED we're buying to do film work is a drop in the bucket with what these LED manufacturers are like doing. I mean, it may be a huge chunk of particular like panel manufacturers, but the people making like the diodes, I mean, you're competing against people who sell LEDs to cover like, like Qatar and stuff like that. Like it's, or like all of Shanghai, so it's just like, there's a scale issue where it's like, I want you to spend a lot of money to make a thing that you're going to probably sell once every 4 years to a couple of, some number of stages. I mean, hopefully with more adoption, there's more of an impetus to do it, but that's largely what we're fighting.
Would we pay more for it?
Yeah.
I don't know.
yeah. I mean, the other real practical issues too on the engineering side, which would be of great interest to SMPTE folks, is it's an exponentially harder thing. It's not linear. Just because you add an extra channel doesn't mean it's just, it's just another thing you have to calibrate for. All of a sudden, it's just like, you're talking about if you have a 3D LUT, all of a sudden you need to have a 4D LUT, and then you have to have, or then you have 5 primaries, then you have to have a 5D LUT. That's 5 by 5 by 5 by 5, that's 5 to the 5th power, so the complexity to every single time you add a channel is exponential. So it's really hard on many different levels to suddenly add an extra channel. So that's the other reason why that there's a lot of resistance to it. It's not because they don't want to, it's because they don't know how to, or it's just,
well, I mean, there's also
hard. Yeah,
you could come in with still RGB and you could output cyan and yellow values too, right? So it could be 3 in, 5 out.
Yeah,
right. Yeah, so there's just so many things that make it difficult, because anything you do to an LED
in terms of regular world experience, like
well, that's what I'm talking about, is just from the manufacturer standpoint, which I have a lot of pain dealing with. Being the manufacturer, is that when you're trying to calibrate for these things, it's really hard, because if you do anything, even if you dim in any method of dimming, you get a spectral change. So even all the matrices that we're used to using, you know, they all assume linearity. So you now have to have a 4D LUT or whatever multidimensional LUT just to maintain linearity, so that all the transforms, everything that we're used to using, would work. But the actual foundation, the mathematical foundation, doesn't work if the system shifts colors. If you change dim, it doesn't just maintain its color. So that's big complexity, and that's why a lot of people, these panel manufacturers, have hard. That's another layer, I'm saying, of the difficulty of adding another primary, even just one extra.
So when Linda, yeah, I was gonna say, when Linda comes on, she's our Mark Shubin. It means that the hook is coming.
I'm afraid so.
Yeah, no, I get that. But one thing I can tell is that there needs to be a second event where we talk about this. There's a lot of,
you know, I agree. There has to be a part 2. And by the way, Tim, it was wonderful to have you come on impromptu. And I hope your children are having a wonderful time.
It's the greatest.
Because we hear
I'm trying my best.
No, hey, listen, let me tell you something. God forbid my dog starts barking. So
Same here.
So don't worry about it. This is wonderful. I don't know if anybody wants to still hang on and have Rafiq keep it going with some Q&A, but we should bring it to a close, just because of fatigue and people want to go about and have dinner. We have some people here. I think, Tony, I may be pronouncing your name incorrectly. Is it Nagai or Nai or Guy? He's here from Hong Kong. So Hong Kong. It's really amazing. And I saw Doug Walker's on from San Francisco, and the people that have been asking the questions, James Blevins, Daquan, really, again, this community is a great community, and it's wonderful to have all of you involved and to hear all of your expertise and your questions. So we are going to have to close it. Greg, do you want to make any allowances for any of these further questions, or what would you like to do?
We don't have time, but certainly I can see there's a huge level of interest, and like I said, typically in our evolution of our business, 1 or 2 things max change. We have like 9 things changing all at one time. We haven't even got into anything like previs and remote production, but clearly there's a lot of work to be done here. ETC has a group, and in addition to these shorts that we make every year, there are different virtual working groups. One of them is on virtual production. Paul's work that he did was based on that work, and we basically take on a task and we get into it. Our goal is to create standards and testing packages where you can send it out to a stage and say, run these tests. Paul created this amazing, the geometry test. He did that because things just didn't look right. Well, he had a solution to that problem, and right away you can tell that things were off. So that work is ongoing. Please ping me offline if you'd like, if you want to get involved in the ETC working groups. We also don't have time to talk about Rapid Industry Solutions, but I just put in the chat, SMPTE.org, Rapid Industry Solutions. It's basically, Brian is actually a working group leader, and we're out to, as the name implies, to develop de facto solutions that are not tied to the standardization process, which obviously it takes a certain amount of time. So we get working groups together with education. We have interoperability. We have outreach, and together we meet and solve a lot of these issues. So look at Rapid Industry Solutions, and you'll find out more about that. With that, I'd like to thank all of our guests tonight: Paul, Zach, Michael, and of course Brian as my co-pilot as always. Thank you for tonight. Linda, do you want any closing comments?
Yeah, again, thank you, Tim Kang, for coming on, and thank you, Rafiq Gagusian, for being our technical director and handling all of this. Greg, you're a rock star. Brian, like I say, I don't know what I'd do without you. Zach, Paul, Michael, Tim, fantastic. Let's do a part 2 because it looks like there's a lot of interest.
Thanks again, everyone.
Great.
Yeah,
have a good night.
Thank you. Bye.
Okay, Rafiq, you can close it up.